Hello friends, welcome to all. Myself Vishal Jogidas. Today we will discuss about breakdown in solid dielectrics, and it is covered in the subject of high voltage engineering. The breakdown of solid dielectrics not only depends on the magnitude of the voltage applied, but also it is a function of time for which the voltage is applied. In this graph we can see in x-axis there is a time and in y-axis there is a breakdown voltage. Now we can see when the magnitude of breakdown voltage is high, at that time the time is very less. So intrinsic breakdown, then avalanche breakdown, thermal breakdown, and last one is erosion or electrochemical breakdown. So in erosion breakdown we can see breakdown voltage is very less but the time is very large. So this is the criteria for this. The dielectric strength of solid material is affected by many factors. Visualization, ambient temperature, then humidity, duration of test, impurities or structural defects, whether AC or DC or impulse voltages are being used, pressure applied to these electrodes, etc. So these are the factors that may affect the dielectric strength of solid materials. However, the time of the application plays an important role in the breakdown process. The various mechanisms are intrinsic breakdown, then electromechanical breakdown, breakdown due to tearing and tracking, then thermal breakdown and electrochemical breakdown. So these are the various mechanisms. Now we will see intrinsic breakdown. If the dielectric material is pure and homogeneous, the temperature and environmental conditions suitably controlled, and if the voltage is applied for a very short time of the order of 10 to minus 8 seconds, the dielectric strength of the specimen increases rapidly to an upper limit known as intrinsic dielectric strength. In this graph also we have seen that here also the intrinsic limit is very high. The intrinsic strength therefore depends mainly upon the structural design of the material. It means the material itself and is affected by the ambient temperature, as the structure itself might change slightly by temperature condition. In order to obtain the intrinsic dielectric strength of a material, the samples are so prepared that there is a high stress in the center of the specimen and much low stress at the corners as shown in figure. This is the specimen designed for intrinsic breakdown. Here we can see in the middle there is a high stress and in corners there is a less stress. So this is the design useful for intrinsic breakdown. The intrinsic breakdown is obtained in times of the order of 10 to minus 8 seconds and therefore has been considered to be electronic in nature. The stress required are of the order of 1 million volt per centimeter. The intrinsic strength is generally assumed to have been reached when electrons in the valence band gain sufficient energy from the electric field to cross the forbidden energy band to the conduction band. In pure homogeneous materials, the valence and the conduction bands are separated by a large energy gap. in a pure materials. At room temperature, no electron can jump from valence band to the conduction band. Okay. The conductivity of pure dielectrics at room temperature is therefore 0. At room temperature, the conductivity of pure dielectric is 0. However, in practice, no insulating material is pure and therefore has some impurities and or imperfections in their structural designs. It means there is no material available for conductivity is 0. The impurity atoms may act as traps for the free electrons in energy levels that lie just below the conduction band is small. So impurity atoms act as a traps for the free electrons. At room temperature, some of the trapped electrons will be excited thermally into the conduction band as the energy gap between the trapping band and the conduction band is small. An amorphous crystal will therefore always have some free electrons in the conduction band. As an electric field is applied, the electrons gain energy and due to collisions between them, the energy is shared by all electrons. Energy is shared by all electrons. Therefore, the temperature of electrons will exceed the lattice temperature and this will result into increase in the number of trapped electrons reaching the conduction band and finally leading to complete the breakdown. So this is the process how the impurity atoms act as a traps and all the processes completes. Now breakdown due to treeing and tracking. We know that the strength of a chain is given by the strength of a weakest link in the chain. Similarly, whenever a solid material has some impurities in terms of some gas pockets or liquid pockets in it, the dielectric strength of the solid will be more or less equal to the strength of the weakest impurities. It means we can say that the dielectric strength of the solid is almost equal to the weakest dielectric strength of the weakest impurities. Suppose some gas pockets are trapped in a solid material during manufacture. The gas has a relative permittivity of unity and the solid material epsilon r, the electric field in the gas will be epsilon r times the field in the solid materials. So as a result, the gas breaks down at a relatively lower voltage. The charge concentration here in the void will make the field more non-uniform. The charge concentration in such voids is found to be quite large to give fields of the order of 10 megavolt per centimeter, which is higher than even the intrinsic breakdown. These charge concentrations at the voids within the dielectric lead to breakdown step by step and finally lead to complete rupture of the dielectric. Since the breakdown is not caused by a single discharge channel and assumes a tree like structure as shown in figure, it is known as breakdown due to treeing. Now we will see the figure of this. Okay. So here we can see there are number of branches like a tree. So because of this, if the breakdown is done due to this. We can say that breakdown due to treeing. The treeing phenomena can be readily demonstrated in a laboratory by applying a impulse voltage between point plane electrodes with the point enabled in a transparent solid dielectrics such as perspex. The treeing phenomenon can be observed in all dielectric wherever non-uniform fields prevail. It means if there is a non-uniform field, then we can see the treeing phenomenon. Suppose we have two electrodes separated by an insulating material and the assembly is placed in an outdoor environment. Some contaminants in the form of moisture or dust particles will get deposited on the surface of the insulation and leakage current starts between the electrode through the contaminants, say moisture. Okay, so due to moisture or dust, there is a leakage current starts in a solid material. The current hits the moisture and causes breaks in the moisture films. These small films then act as electrodes and sparks are drawn between the films. The sparks cause carbonization and volatilization of the insulation and lead to formation of permanent carbon tracks on the surface of the insulators. Okay, due to moisture, there is a track will be there, and this track will be becomes permanent due to some chemical processes on this. Therefore, tracking is the formation of a permanent conducting path, usually carbon across the surface of insulation. For tracking to occur, the insulating material must contain organic substances. The rate of tracking can be slowed down by adding filters to the polymers which inhibit carbonization. So this is the tracking. So in solid, breakdown may be done due to treeing and tracking. Thank you.